Hello and welcome back. Today we're continuing our saga of model evaluation and we're talking about adjusted R-squared. Previously we discussed R-squared, which is defined as 1 minus the residual sum squared divided by the total sum squared, and R-squared is a goodness of fit for our models. Greater is better. Just a quick reminder, we mentioned that R-squared is between 0 and 1 and that there is no overarching rule of thumb. The values really depend on the industry and use case. So for some industries and use cases, 0.9 might be a great R-squared and 0.4 might be a terrible R-squared. For other industries and use cases, 0.4 might be a great R-squared. So it really depends. However, there is an overarching problem across the board, which is to do with adding new independent variables. So let's say we have a linear regression with two independent variables and we decide to add a third one. For example, we got new data, a new column of data, or we're just trying to explore and see what other variables might be helpful in the explanation in our model. So what happens when we add another variable is that the total sum of squares doesn't change because it only depends on the average of the y actual values and doesn't depend on the y hat values. But the residual sum of squares will change, and in fact, it will only either decrease or stay the same. The problem we're facing is that the residual sum of squares will never increase when we try to add another variable. And this might not be intuitive at first, so let's talk about it a little bit. The main reason for this is that we are using the ordinary least squares method to build our models. And what the ordinary least squares method does is it aims to minimize the residual sum of squares. So let's try see this in action. When we add this new variable, x3, the ordinary least squared method is going to look for coefficients b3 that improve the yi hat predicted values. As long as it finds a coefficient b3 where the yi hat values are better than they were before, closer to the actual values, then the sum of the residual sum of squares will improve. It could improve by a lot if the prediction is much better now, or it could improve by a tiny little bit even if the prediction is a little bit better. Now, in the situation where the ordinary least squares method cannot find a coefficient b3 that improves the predictions, like all possible coefficients b3 make the predictions worse, then the ordinary least squared method is just going to be very smart or sneaky, you can call it, and it's just going to turn b3 into 0. It's just going to say, okay, we're going to set b3 at 0, and that means even though we technically added an extra variable, it's not participating at all in the predictions because its coefficient is 0. So in that case, the residual sum of squares won't change, will be exactly as it was before. So we end up with a situation where we can just keep adding more and more variables that maybe have even nothing to do with our problem at hand, but by virtue of some random correlations, our R-squared in some cases will be improving. It never gets worse. So the residual sum of squared will decrease. That means R-squared will increase. And that's a problem because we don't want to end up with models that have lots of variables that have nothing to do with that model, that are not really adding a lot of value, but in general are just increasing R-squared. So what is the solution? The solution is a new version of R-squared, an adjusted R-squared, and that's exactly what it's called. It is calculated with this scary looking formula, but as you'll see from the practical tutorials with Adlan, it's not scary at all, and you'll be able to recreate this actually manually. So here there are a couple of new parameters. K is the number of independent variables that are in our model, and N is the sample size. And the important thing here is to look at K. So if K increases over here, then the denominator decreases. That means the whole ratio increases. And because it's been subtracted, that means adjusted R-square decreases. So that's the important point here, that this new formula penalizes us for adding additional variables. So basically it's only worth adding an extra variable if R squared, this original R squared, if it increases substantially enough that compensates for this penalty. So adding new variables becomes something that has to be justified. If it's not justified, then the new variable is not worth adding. And that's what adjusted R-squared is about. It's about making sure that we only add variables when they bring substantial improvement to our model. So there we go. That's adjusted R-squared. Hope you enjoyed this tutorial, and I'll see you next time. Until then, enjoy machine learning.